Hello and welcome. You've probably seen this before, right? You're reading a study and you see that little phrase, p is less than 0.05, and you kind of nod along. But what does it actually mean? Well, today we're going to demystify one of the most important and maybe misunderstood concepts in all of statistics, the p-value.
So let's just jump right in with a puzzle. Imagine we run a salary survey, and our data shows that, on average, men are earning 150 euros more per month than women. The big question is, did we just find a genuine, real-world pay gap? Or could this difference just be a random fluke? Something that popped up by pure chance in the specific group of people we happen to survey. And that right there is the fundamental challenge in so much research. Any set of data you collect is going to have some random noise in it, some natural variation. So how do we tell if the signal we're seeing, that 150 euro difference, is a real thing or if it's just part of that random background static? We need a tool to help us decide. And that tool, my friends, is the p-value. It was literally designed for this exact job, to help us figure out if what we're seeing is a real effect or just the luck of the draw. Okay, so here's the official textbook definition. The p-value is the probability of getting your result, or something even more extreme, if the null hypothesis is true. Right, I know, that sounds super academic and a little confusing, so let's throw that away for a second and think about it in a much more intuitive way. The absolute best way to think about a p-value is as a surprise meter. That's it. It just measures how surprising your data is. But, and this is the key, it measures the surprise assuming that nothing interesting is actually going on. So a low p-value is like your meter screaming, whoa, this is a really surprising result if there's no real effect. And a high p-value is just a shrug. Like, meh, this isn't surprising at all. This could totally happen by chance. Okay, but before we can use our awesome surprise meter, we got to set up the rules of the game. And that means we need two really important ideas in place, a starting assumption and a standard for what we consider surprising.
First up, our starting assumption. In statistics, it's called the null hypothesis, but just think of it like a courtroom, innocent until proven guilty. This is the boring, default position. We assume there is no real salary gap. The exciting new idea we want to test, that a gap does exist, that's the alternative. We're going to stick with the no gap story unless the evidence against it is just overwhelming.
Which, of course, leads to the next logical question, right? How strong does that evidence have to be? What's the tipping point? Where do we draw the line and say, okay, yeah, I don't believe that no different story anymore? Well, in science, we actually decide on this before we even look at the p-value. We set a threshold for surprise ahead of time. And the most common threshold, which we call the significance level, or alpha, is 5%, or 0.05. This is our pre-agreed upon line in the sand. It's our beyond a reasonable doubt for the data. We're basically saying, look, if the result we find is so rare that it would only happen by chance less than 5% of the time, then that's surprising enough for us to sit up, take notice, and reject our initial no difference assumption. All right, so we have our rules, we have our starting assumption, no salary gap, and we have our threshold for surprise, 5%. Now let's go back to our data and make the call. So we run the numbers on our survey, we do all the calculations, and the p-value for that 150 euro salary difference turns out to be 0.04. So what on earth does that number mean? Well, let's translate it using our surprise meter. It means that if there were truly no salary gap in the world, the probability of us just happening to find a difference of 150 euros or more in our random sample is only 4%. That's pretty unlikely. It's a pretty surprising result. So now for the moment of truth. We take our p-value, 0.04, and we compare it to that 0.05 line in the sand we drew earlier. And since 0.04 is less than 0.05, our finding crosses the threshold into what we call significant. Because our result was more surprising than our 5% threshold allowed for, we can finally make our decision. We are going to reject that boring no difference assumption. We can now officially announce that our finding is statistically significant. Okay, so that was a lot, but we can actually boil this entire process down into a simple, repeatable checklist. Let's just do a quick recap. It really all comes down to these 5 steps. First, you set your standard of proof, our 5%. Second, you state the no effect story, no salary gap. Third, you go get your data and calculate that p-value. Fourth, you compare your result to your standard. And finally, number 5, you make the call. If it's surprising enough, you reject the no effect story. That's it. That's the core logic right there.
But, and this is a huge but, there is one last, incredibly important piece of fine print we need to cover. Because significant result, well, it isn't the same thing as absolute proof.
Look, it is so important to get this right. A p-value of 0.04 does not prove there's a salary gap. It just gives us strong evidence that the no gap story is pretty unlikely. Statistics is all about probabilities, not certainties. And remember that 5% threshold we set? That also means that, over the long haul, we accept that we're going to be wrong about 5% of the time. We'll claim a result is real when it was just a fluke. It's a calculated risk we take to be able to learn from data.
So let's bring this all home for one final crucial takeaway that you should always keep in mind.
So, we did it. We concluded that our €150 salary gap is statistically significant. The math tells us it's probably not a random fluke. But here's the question I want to leave you with. Is it practically significant? Is a €150 difference actually big enough to matter in the real world? The p-value can't answer that. It can only tell you if an effect is likely real. It can't tell you if it's important. And that is a massive distinction.